So hi everyone, welcome to our second talk of the NCU-Delta online talk series. I'm Yan Chen, your host tonight. So sorry I have to do the same introduction every time since there might be some new audience. So for those who haven't heard it before, this talk series will be given by all awardees of NCU-Delta Young Astronomer Lectureship Award. And this award was established by National Central University and Delta Electronics Foundation to recognize young scholars under the age of 45 who have made outstanding contribution in this field. So each year, the awardee will be invited to Taiwan to interact with the local astronomers and the public. So I think the first award was given in 2012, which is almost 10 years ago. So the original plan for this year was to hold big event for, by inviting all the previous awardees to come to Taiwan to celebrate. But things have been difficult due to this COVID-19. So we have decided to make this online, unfortunately. But the good thing is, probably more people can join this event, which is not limited to the people in Taiwan. So our speaker today is Professor Chris Reynolds from the University of Cambridge. So it's our great pleasure to have him here. So Chris received, I think you received this award in 2013. Yeah, and now is a premium professor in the University of Cambridge, right? Which is a very prestigious professorship, which included many big names like Eddington Martin Rees. Yeah, I Googled this, Richard Ellis and Robert Kennicott. Those are very big names. So Chris is like a world-renowned expert in accretion and jets of supermassive black holes, from GR magnetohydrodynamic simulations of black hole accretion disks to AGN feedbacks in galaxy clusters. And his works involve both numerical simulations and X-ray data analysis. And I believe he was one of the pioneers in using X-ray like iron lines for measuring spin of black holes, and in using X-ray variability to infer the coronal properties in accretion disk systems. So I have to admit that I actually borrowed this very nice introduction from Karen. So, so who is now professor at National Tsinghua University, because she's a very close collaborator of Chris. So thank you very much, Karen. So, so today, Chris is going to talk about this very exciting black holes. Just Chris, I'll let you take this away. Can share your screen.
Thank you very much, Yin-Chen. And so, yes, so thank you very much for such a nice introduction. And thank you for the invitation to give this talk. I'm very sorry I can't be there in person. I remember with great fondness my visit to NCU back in 2013. I don't know if you've got eagle eyes on the video, but I actually have the award on my cover back behind me. I look forward to one day visiting again. So today I'm going to start off by I'm going to be telling you about some work we've been doing on what is really quite a basic and fundamental question, which is, why do accreting black holes vary? Why do they vary in time? And let me just start off with a broad introduction to accreting black holes, and I'll tell you why this is actually an interesting question that we've been looking at. But firstly, the broad introduction. If you look out into the universe with, say, the Hubble Space Telescope, you look out with optical eyes, then you see a universe full of galaxies and full of stars. So this, of course, is the famous Hubble Deep Field. Essentially, everything you're seeing here is a galaxy. There's maybe one or two stars in this whole image. But essentially, everything you're seeing is a galaxy, many of them very distant galaxies. And yet the actual light you're seeing here is all starlight. It's all starlight from the galaxies, the stars in the galaxies themselves. Now, if you actually stare out in the universe with an X-ray telescope, you can actually get a very, very different view of it. So if we now go to the Chandra Deep Field, this is from the Chandra X-ray Observatory, you get this field of looks like a field of stars. In fact, every single point here is thought to be a black hole, or more precisely, an accreting black hole, an accreting supermassive black hole, sitting at the center of a galaxy. So the X-ray sky is dominated by these so-called active galactic nuclei. Fundamentally, what we believe is the power source of these objects is gases falling into supermassive black holes. The black holes can have a vast range of masses. The small ones are a mere 100,000 times the mass of the sun, but that can go all the way up to billions of solar masses. So they can have a huge range of masses depending upon the galaxies they sit in. And if you do a count, you count up how many AGN we see when we look out, and you count up how many galaxies we see, we find that about 1% of galaxies actually host one of these powerful AGN. And in their extreme cases, the AGN can actually outshine their galaxy by some extreme factors of 100 or even 1,000. In the extreme case, the energy coming out of these centers of these galaxies can be vastly more than the energy in all the stars put together. Now, many of the AGN we see in this particular image, for example, are actually rather distant objects. So many of them will be, 6 or 7 billion light years away. So when the universe was half its current age. But we don't have to look out at such extreme distances to find these objects. This is one particularly nice example. This is the Centaurus A galaxy, which is really on our doorstep. And what we have here is another example of one of these powerful active galactic nuclei. So at the very center of this galaxy, we believe that there's a supermassive black hole, probably in the billion solar mass range. And there's a tremendous amount of X-ray emission coming from this object that we can see if we look with X-ray telescopes. We also see in this particular example another phenomenon that's quite common, which is that there can be powerful jets coming out of the center of these objects. So some process associated with gas falling into the black hole can produce jets of matter that are squirting out of the center of the galaxy. Principally are seen via radio emission that they create. So these are called radio jets and radio galaxies. But this is another way that energy is released from the core of this galaxy. It can be released as the kinetic energy of material that is being ejected from the centers of these galaxies. So this is the phenomenon of active galactic nuclei. So if we were to zoom in on the very center of one of these objects, see exactly what's going on, what we might see is something like this. We have the supermassive black hole itself at the very center. Of course, this is a massive object with extremely strong gravitational field. So by the time you actually get up to the event horizon, the escape speed is the speed of light. And in these active galactic nuclei, there is gas that's falling into them. They fall in via this accretion disk, so the gas spirals into the black hole. As it does that, it is releasing energy. It's giving up its gravitational energy. This is a process that is very akin, actually, to hydroelectric power. So in hydroelectric energy, we have water that is falling down some distance. It's falling off a dam, for example. And if we were to put turbines in the way and extract the energy from it, we can actually power generators. So we can actually extract the energy as water is falling down some slope. Well, in fact, we can get energy out of black hole systems in very much a parallel way. We have matter that's falling towards the black hole. It will be giving up gravitational energy. The difference compared to the hydroelectric dam is just the amount of energy that is being given up. Of course, Einstein's famous formula, E equals mc squared. This tells us that there can be a conversion of mass into energy. And what we find is if we, for example, drop 1 kilogram of matter from a large distance into a black hole, we can convert about 10% of that 1 kilogram into energy. So the efficiency is about 10%. And that translates into the equivalent of about 2 million tons of TNT exploding. So dropping 1 kilogram into a black hole releases the amount of energy that a very sizable nuclear weapon would release. So this is an incredibly efficient process. And then, of course, in these active galactic nuclei, we're not dropping 1 kilogram in. We are dropping, many. We can drop many solar masses per year into the black hole, and that's what generates the extreme energies. So that's the fundamentals of how an active galactic, of what the active galactic nuclei are. Now, this talk is going to be focused on the variability of active galactic nuclei. And this is actually a huge topic. There's many different facets of the variability. We know that active galactic nuclei must turn on and turn off. One way we know that is that if they didn't turn off, and they just had this amount of matter pouring into them for the age of the universe, the black holes would be vastly larger than what we actually see. But we can also actually see direct observational evidence for black holes turning on and off. This is one example. This is the Hercules A radio galaxy. And again, here we have in the red is a radio map of this galaxy. And in the white is the background optical image, but you can see in the jet that it very much looks like the jet is stopping and starting. So we have the jet is flowing outwards, but it looks like there's different events here, different series of ejections down the jet. And we believe that indeed in some of these systems, that's what's going on. The jet is stopping and starting, stopping and starting on time scales of 10 to the 5 to 10 to the 6 years. So this is one example of how active galactic nuclei are can vary. But the variability I'm going to focus on in this talk is the much more rapid variability we see. And this is one of these amazing facts of active galactic nuclei, that they can change their power output incredibly quickly. So this is one particular active galactic nucleus. It goes by a very unmemorable name of IRAS 13224. And this is a light curve from that object from the XMM Newton Observatory. So it's an X-ray light curve. And the top panel here is our soft X-rays, so low energy X-rays. The bottom panel is hard X-rays. And this whole trace is only about a week long. So one day is this bar up here, this red bar. And you can see that this object is tremendously variable. There are flares in this object where it can double in power and then halve again in only an hour or two. So that the length of this talk, the AGN can double its energy output and then have it drop again. And remember, there's the amount of energy coming out in this particular object in the X-rays is actually comparable to the total stellar output of the whole galaxy. So you have this amazingly powerful object that is modulating its power on really very, very short time scales. And the focus of this talk is going to be the question, how does it do this? What is going on that's driving this kind of very rapid variability? So that's going to be the focus of this talk.